Okay, so here's a Zoom meeting for Physics 231 C. We just finished the second midterm exam. And also the corrections for the midterm exam. I'll send out a feedback on the exam later, not today. Now, the next subject is gravity. That's chapter 9 in the textbook. So you should be reading chapter 9. It's an important chapter because it's a very basic example of the concepts we've been studying. We've studied about forces and energies. Well, a particularly important force is the gravitational force. And there is corresponding to that gravitational energy. And it has a lot of applications, not so much in everyday life. Well, gravity affects our everyday lives, obviously. But what we're really interested in, I mean, the Earth's gravity, we tend to think of Earth's gravity as very strong, but that's because we're experiencing the gravity of the whole Earth. Earth's gravity between laboratory-sized objects is actually quite small. In fact, it was very difficult to measure Newton's gravitational constant. That was done by Henry Cavendish some years after Newton had already died. So measuring gravity is actually rather difficult, but it can be done in the laboratory with a very clever experiment and precise experiment. But what we really want to see is how Newton's theory of gravity explains the motion of the planets in the solar system. That's what made Newton famous, was that he was able to describe the motion of the planets. The motion of the planets were known before Newton. They had been measured and accurately described by Johannes Kepler, a German physicist, mathematician really, who lived before Newton. But what was not known after Kepler's work is why the planets move in the way they do. Kepler discovered how they move very accurately. We still use Kepler's laws today to describe the motion of the planets. But it wasn't until Newton that it was explained why they move the way they do. And the important formula that Newton devised, called Newton's law of gravity, or Newton's theory of universal gravitation, is described by this equation. The force between two masses, suppose you have two masses, M1, M2, separated by a distance r. Well, it's an interaction. So consistent with Newton's third law of motion, there are equal but opposite forces. Both masses experience a force directed towards the other mass. And the two forces are equal. They're equal but opposite. So we could say F1 as a vector is minus F2 as a vector. The negative sign says that the two vectors in opposite directions. A vector is a mathematical quantity with a direction and an amplitude. Well, they have opposite directions and they have equal amplitudes. So F1 magnitude is equal to F2 magnitude. And that force magnitude is what's given by this equation. There's a universal constant G, which is the same for any two masses in the universe. It's the same for the Earth and the Sun. It's the same for the Earth and the Moon. It's the same for the Earth and you. It's a universal constant, and that's called G. Then there's the product of the two masses, say the mass of the Earth and the mass of the Sun, or the mass of the Earth and the mass of the Moon, or the mass of the Earth and you, your mass. That's the numerator here, divided by the distance squared. Now, if we think of these masses as being spheres, R means the distance between their centers, like in this picture. If it's the distance between the Earth and you, well, it's the distance between the center of the Earth and, say, your belly button, the center of your body. That's the universal theory of gravity, published by Newton. He worked out this theory when he was quite young. He worked out this theory when he was staying on his mother's farm. He had to leave the University of Cambridge in Cambridge, England, because there was a bubonic plague epidemic. So it's just like when we had the pandemic a couple of years ago, everybody had to go home. When they had the bubonic plague, everybody had to go home. So he went and stayed with his mother and father-in-law. His mother and her husband on their farm, and he wasn't going to catch the bubonic plague because there weren't any other people around on the farm that he could catch it from. During that time, he didn't have much to do. He didn't like working on the farm, so he worked out the theory of motion and gravity. But he was very young and he wasn't willing to publish it. In fact, he didn't publish the theory until much later. So it was discovered during the year of the bubonic plague, 1666 to 1667. It was published in the great textbook Principia around 1687, 20 years later. And of course, in those days, they wrote scientific books in Latin. It wasn't published in English until 1728. That was actually the year after he died. It was translated from Latin into English. And this discovery made Newton the most famous scientist of his time, because it explained why the planets move around the sun in our solar system the way they do. Many years later, in 1916, so what's that? More than 200 years later, Albert Einstein published the general theory of relativity, which replaced Newton's theory as the best theory of gravity, and kind of provided a theory of space, time, and gravity. Rather different than Newton's theory. In Newton's theory, space and time were absolutes. In Einstein's theory, space and time were relative. And in Newton's theory, gravity was a force. But in Einstein's theory, gravity is an effect of the curvature of space-time. So Einstein's theory is rather different than Newton's theory. However, Newton's theory is not obsolete because it is extremely accurate. So, for example, NASA relies on Newton's theory to calculate planetary orbits in the solar system and satellite orbits when they put satellites in orbit around the Earth or around the sun or in solar system exploration. Newton's theory is perfectly accurate enough for NASA's purposes. It isn't necessary to take Einstein's more perfect theory unless the gravitational force is extremely large. Like, for example, the force associated with a black hole. So, or unless the measurements are being made extremely accurate. So Einstein predicted a minor change in the orbit of the planet Mercury, which was verified. And that provided one of the first pieces of experimental evidence that Einstein's theory of general relativity is correct and not in agreement with Newton's theory. Now, we're not going to talk about the theory of general relativity. That's a very advanced mathematics. So we will be studying in chapter 9 Newton's theory of gravity. And we'll be using the general concepts of force and energy that we've developed earlier in the semester. All right, so that's sort of the background for chapter 9. Now you have to read chapter 9. The problem assignment is not due for a while. So you've got about a week, more than a week actually, to do the problems associated with chapter 9. You should start doing it now because chapter 9 is a long chapter. And there are a lot of different example problems. All right, so let's take a look at some problems that you can solve using Newton's theory of gravity. Here's a problem which has to do with the measurement of g, that universal constant. So this is a problem, I don't think it's problem 2039. That's got to be wrong. It's got to be problem 939 probably. It's the problem from chapter 9, problem 39. The measurement of g was first done by Henry Cavendish in 1800. He was a British aristocrat and became a famous scientist, really. This was one of his great achievements, was to measure g. In a typical Cavendish experiment, 2 small lead balls on a rod are attracted to 2 large lead balls as shown in a figure. Here's a picture that shows, well, here's a picture I drew myself. Given the data below, find the attractive force between one small ball and the nearer large ball. And part B, find the torque on the rod. So here's a picture of Cavendish's experiment. There were two lead balls attached to a rod, which is suspended from the ceiling, very delicately balanced. So that's called a torsion balance. Now, you place near these two balls two large lead balls, which will attract the smaller lead balls. So we have two spheres with mass m that are small, and two large spheres with mass capital M that are large. And Cavendish, by very delicate methods, would place the torsion beam or the torsion balance at rest and then let go. And the small ball or the small sphere would be attracted to the nearest large sphere. It would also be attracted to the other sphere because gravity is universal. But the importance, the most strongest force would be the attraction to the nearer sphere. There would be equal but opposite forces on the two ends of the balance. And so the balance would experience a torque. And we know from chapter 8, torque produces angular acceleration. And Cavendish would observe this angular acceleration. So his measurement was a measurement of angular acceleration. And he wanted to compare that to Newton's theory, which is that the force is gmm over a distance squared, not this r, but this distance d, the distance between a small sphere and a large sphere. That would be one of the forces. The torque would be that force times r, which is the distance from the axle. So here's the axle. It's a little filament by which the torsion balance is suspended. So that's r times 2, because there are two contributions to the torque. There's a contribution at both ends. So the torque will be gmm over distance squared times r times 2. And that will be the moment of inertia times alpha. And again, a very delicate experiment. Cavendish would measure alpha. And knowing the masses and the distances and the meaning of moment of inertia, the only unknown is g. And he found that g is, well, this is a modern value, 6.67 times 10 to the minus 11 in standard units. That's a very small number. It has 11 factors of 0. That's 0.0000000000667. Now the problem here, which is assigned in the assignment, is to calculate, well, part B is to find the torque. Using what we know now to be the Newtonian gravitational constant. All right, so that's a laboratory example of Newton's law of universal gravitation. Here's another problem. I don't think it's problem 2053. It must be problem 953 from chapter 9. How to send a satellite from the Earth to Mars. The best way to send a satellite from the Earth to Mars, best meaning using the least energy, so the least amount of fuel, is to put it on an orbit called the Hohmann ellipse. The Hohmann ellipse is the trajectory of the satellite going from one planet to another that requires the least energy. So here's a picture of the problem. We always draw a picture. Here's the sun at the center. There's the sun. Here's the Earth in orbit around the sun. And so the satellite starts over here at the Earth. Now it is placed onto an orbit in which it revolves around the sun. When it's far enough away from the Earth, you can neglect the effect of the Earth. And the only force on it is the gravitational force exerted by the sun. It'll then travel on an elliptical orbit where the sun is at one of the focal points of the ellipse, and it will arrive at some maximum distance, which you make equal to the distance from Mars to the sun. So you see, as the satellite travels from Earth to Mars, traveling in orbit around the sun, it goes from a distance r1, which is the nearest it comes from the sun, to a distance r2, which is the farthest away it'll reach the sun. You want r1, that's the perihelion, to be the distance from the sun to the Earth. You want r2, that's the largest distance, or the aphelion. You want that to be the distance from the sun to Mars. And you want it to arrive at that distance r2 at the same time that the planet Mars arrives at that point. So now it will be affected by the gravity of Mars, and it will fall into Mars, and you've landed on Mars. So that's the Hohmann transfer orbit. It's 1/2 of this ellipse. It was first worked out by a German named Walter Hohmann in about 1925. That's before there weren't any rockets. There weren't any rockets in 1925. It was other scientists later who developed rockets, like Werner von Braun. The rocket is needed here to put the satellite in a large orbit, and it's needed here, retro rockets, to slow it down and stop it so that it doesn't continue on its orbit around back to the Earth. You want it to stop at Mars. So the perihelion is the distance from the Earth to the sun. That's 1 astronomical unit. And the aphelion is the distance from the sun to Mars. That's 1.52 astronomical units. The semi-major axis of the ellipse is 1/2 r1 plus r2. The major axis is the distance from the Earth to Mars in this configuration. In other words, it's the large diameter of the ellipse. The semi-major axis is 1/2 of the major axis. It's kind of the large radius. Not really radius, because the ellipse is not circular. It's elliptical. Now, the motion of masses in orbit around the sun are described by Johannes Kepler, the 3 laws of planetary orbits. The first law says the orbit is an ellipse. Okay, so it'll have a perihelion and an aphelion. Kepler's third law says that the period is proportional to the semi-major axis to the 3/2 power. In other words, the period squared divided by the radius cubed, that's the elliptical radius, the semi-major axis, is the same for all the masses that are in orbit around the sun. It's the same for the Earth, it's the same for Jupiter, it's the same for Neptune, it's the same for this satellite, which is traveling from Earth to Mars. So p squared over a cubed for the Hohmann ellipse is equal to p squared over a cubed for the Earth, or for Jupiter, or for any other mass in orbit around the sun. Well, we can easily write down p squared over a cubed for the Earth. It's equal to 1 if we use the right system of units. P, the period of the Earth around the sun, is 1 year. So that's 1. A, the distance from the Earth from the sun to the Earth, is 1 astronomical unit. That's the definition of the astronomical unit. So p squared over a cubed is 1 divided by 1. It's 1, but you have to be careful about the units. The units are years in the numerator squared and astronomical units in the denominator cubed. So now what's the question? What's the travel time? What's the time? So we're supposed to be calculating the travel time. Well, the trajectory is from the Earth to Mars on this Hohmann ellipse. So we want half the ellipse. So the travel time is 1/2 the ellipse. Now the total time for the ellipse is p. This p here. And we know this p here, I guess. All right, so that's an example of using Newton's theory of universal gravitation to explore the solar system by NASA. Here's another example that would be relevant to NASA. A satellite is in a circular orbit 1,000 kilometers above the Earth's surface, and it has a total mechanical energy, E. What's its kinetic energy? What's its mass? And what's its speed? And what information are you given? The total energy. Total energy is minus 1.1 gigajoules. A gigajoule is 10 to the 9th joules. So we always start a problem by drawing a picture. So here's a picture. Here's the Earth. The Earth is blue. Everybody knows the Earth is blue because you've seen photographs of the Earth from space. It's blue because mostly it's water. The Earth has a radius r sub e. That's 6,371 kilometers. That's the radius of the Earth. Here's the satellite, 1,000 meters above the surface of the Earth. So let's call h the distance above the surface of the Earth, 1,000 kilometers. So, here's the Earth, its radius is 6,400. Add another 1,000, that'll give you the radius of the satellite's orbit because it's in a circular orbit. So the radius of the satellite's orbit, that's this radius, r, is the radius of the Earth plus h. So it's 7,371 kilometers. All right, there's the picture. Now here's the problem. It's problem 77. I don't know why this keeps saying 2077. It must be 9.77. Chapter 9, problem 77. Well, the satellite is moving around with some speed v. The kinetic energy is a half mv squared. The satellite has a mass m, which is given. No, m is something you're supposed to calculate. So m is not given. So the kinetic energy is 1/2 mv squared. What's the mass here? Well, I don't know. I'm not given the mass. So I have to have another formula which expresses the mass that I will need. And one of the equations you'll find in the textbook is that the energy of a circular orbit is minus gmm over 2r. The energy is negative because it's bound to the Earth. If it were going to escape to infinity, it would have to have a positive energy because it would have positive kinetic energy if it escapes. But if it's not going to escape from the Earth, it's just going to be in orbit around the Earth, then it has to have a negative energy. And for a sphere or a circle, the energy is minus gmm over 2r. Well, I can solve that. I mean, I can replace that by an equation for m, 2re over gm. Now, E is given, G is universal, M is the mass of the Earth, little m is the mass of the planet. That's one of the unknowns. So, I have various equations. And I have to put those equations together. I have to solve simultaneous equations for the three answers to the problems: kinetic energy, mass of the satellite, speed of the satellite. So that's A, B, and C. So, we always draw a picture, label the picture with various parameters, not the actual values, but just the symbols to stand for those values. We write down the equations. Here's the equation for Newton's second law for a planet in a circular, or a satellite in a circular orbit. So that's Newton's second law. Newton's second law of motion. The mass times the acceleration is equal to the force. Well, the acceleration is v squared over r because it's a circular motion. So that's the centripetal acceleration, v squared over r. Now, what's the force? The force is the force of gravity, gmm over r squared. So, for example, the m's cancel, the little m's cancel, 1 power of r will cancel, so I can write down an equation for the speed. The mass of the Earth is something you have to look up in the book. Well, actually, to help do the calculations, you can notice that g times m is the same as g at the surface of the Earth times the radius of the Earth squared. So since this involves gm, you don't actually have to look up the mass of the Earth. You don't even have to know the mass of the Earth. You just have to know the value of gm. And gm is gr squared, 9.81 times the radius of the Earth squared. The radius of the Earth we do know. And r is 7,371 kilometers. So this calculates v. E you can relate, and E is given. You can use that to determine m once you've figured out v. No, you don't even need to figure out V. Use that to calculate M, and you can put those two together to calculate the kinetic energy. So it's the usual kind of problem where you have certain equations, you have multiple equations and multiple unknowns. So you have to use algebra. Isn't that the one I just did? That's the one I just did. So I guess that's all I have. I have the Cavendish experiment, the Hohmann ellipse, a satellite in a circular orbit. And I guess this one's the same satellite in a circular orbit. So I've got three problems here. So you'll have a bunch of problems like this in the homework assignment, which I guess is due. Let's see, this is Friday. I think it's due a week from Monday. So you have a little while to work on it. But in the meantime, read chapter 9.